All right, so just a reminder of what we covered last time. We defined what a parametric curve was. It's just a new way to define a point in the plane instead of defining it as just an xy coordinate. We introduce a third parameter. We'll call that t. It doesn't have to be t. It could be any other parameter. And you define the x as a function of that third parameter, the y as a separate function of that third parameter, and that gives us the ability to sort of explore these curves that aren't necessarily functions of just x or y, but functions of a third parameter. Okay, and we call the pair of equations parametric equation. The new variable that x and y are independently functions of is called the parameter. And then the curve that gets traced out is called a parametric curve. Did a couple examples of that. Now, to be able to trace out a curve, we can't just extend it indefinitely. A lot of times these, sometimes, I shouldn't say a lot of times, these can have behavior that varies wildly, infinitely. So we have to decide what part of the curve do we want to look at, define the parameter in between those endpoints. And so then we have what's called an initial point, which would be f of a, g of a, and a terminal point, f of b, g of b. And when you graph these, you kind of want to indicate the direction that it's being graphed, because it does have a direction, as you can see in my calculator, or in your calculator. When it traces out, it's tracing out between your t-min and your t-max. So it's starting at t-min, which it's getting its initial point for, and it's ending at your t-max, which it's getting your terminal point from. And so then we found out, oh, we've actually had some experience with parametric equations. We just were used to seeing as x equals cosine theta, y equals sine theta, where theta was our parameter. But if we replace theta with t, we can see that what gets traced out, if I let t vary between 0 and 2 pi, is just the unit circle. And this gets traced out in a counterclockwise direction. All right, and then we did some exploration with our graphing devices. And now we are on the cycloid. So I'm going to have you draw out this diagram, because we're going to use this diagram. We're going to do a little bit of a geometric construction here. So it's been a while since you've done that. I don't know if we've ever done that. Although I guess you could say constructing the unit circle is that. But a cycloid is produced when we focus on a circle and a point on that circle, and we follow the path that's being traced out by that point as we roll the circle along an axis, right? And so that curve is called a cycloid, and it actually has some really interesting physical properties that I'll try and illustrate for you. But first, let's have you draw out this diagram. So make it large enough, you know. We're going to be using all of these labels. So I'm going to pause my recording and so let's try this in our calculator. Grab your calculator. Let's just set the radius to 1 for now. So we'll say we're dealing with the unit circle. So if I'm dealing with the unit circle, my radius is just 1, and then I'll do t minus sine t. Remember, the name of the parameter doesn't matter. In this case, our calculator just makes it t, but t represents the angle that our circle is following, right? And y is 1 times 1 minus cosine t. Okay. And if we look at our window, let's say I just let it roll for one rotation, one cycle, so that's just going to be 0 to 2 pi. I'm going to make my t-step smallish. And then I'm just going to start looking at the origin. Now the highest it'll ever go is 1, right? If you think about it tracing along the circle. Let me go back here. No, that's not true, is it? So if I make the radius 1, the highest it'll be is at this point. We're following that point. When it rolls to the top of the circle, that'll be 2 of the radii. So the cycloid itself will actually go up to 2, right? And down to 0. So that'll kind of inform my choice of window. So it'll go all the way up to 2, so, and down to 0. My x max, though, this is the horizontal direction, so if it goes 1 full rotation, it's also only going to go out to 2, I believe. So I'm just going to go to 4. All right, y-min, negative 0.5 just to give a buffer, up to 2.5 just to get a buffer. All right, so let's take a look. Oh no, I misread my. So let me think about this. Hold on. If we're tracing out a full rotation of the circle, so it starts at the origin, it's going to go up to the top at pi. I underestimated what my x window should be. Here, let's just do this the easy way. Let's just go out to 10. All right, but if I go only to 2 pi, I get 1 basically arc of my cycloid, right? So let's change our Tmax. Let's say we want 2 arches, you would do 4 pi. If you want 3 arches, you would do 6 pi, and so on, right? All right. So a couple of things about the cycloid. Said there were some kind of interesting facts about it. So a cycloid can be created with any size radius, and they'll sort of have different shapes. So I have this little app that'll allow me to trace out the cycloid. So you can kind of see the cycloid being traced out as I roll the circle. So that's if we follow the cycloid on the edge of the circle, but you can also just follow the cycloid on some other part of the radius. Let's say if I make it bigger than the circle, then you're going to get, oh, come on. You're going to get a cycloid that sort of loops around itself. Or smaller than the circle, it won't come all the way down and hit the x-axis, right? So this is called a curtate cycloid, and the one where you're following a point along the radius but outside the circle. It's called a prolate cycloid, and then one that's just on the circle when it's just the radius of the circle. You just have a cycloid, a regular old cycloid. So one interesting thing about the cycloid, it's a solution to a famous physics problem called the Brachistochrone problem, which was if we had an arch, like a physical arch, or not even an arch, hold on. Sorry, if we had 2 points, one above the other, but they're offset, call this one point A, and this one point B. What's the fastest way you can move a particle? And so this is in real life, like under the effect of gravity. What's the fastest way you can move a particle from point A to point B? And so the fastest way, so you might go, well, what if you had like a ramp? Let's say you just put a ramp underneath them that's linear, that connects point A to point B. And under the force of gravity, you let this little cylindrical particle, this BB, roll from point A to point B. Is there any way to get it there faster? Like, is there any curve that's going to be faster than just this linear ramp? And the answer is yes. The fastest way, the solution to this happens to be an inverted cycloid. So an upside down cycloid is the fastest path. And so beyond that, this is actually the solution to this, because this is the solution to what's called the Tautochron problem, which basically says that no matter where you place these particles, so if I placed another particle here, let's call that A2, and another one here, let's call that A3, and another one here, let's call that A4. These are actually all going to reach point B at the exact same time. And that's because if I continue that inverted cycloid, one physical property of the inverted cycloid is that these BBs, or these particles, will complete one cycle in the exact same amount of time. Now, they won't complete the same distance, like their cycles won't necessarily be the same distance, so A4 isn't going to roll up this side of the cycloid as far as, say, the first A is. This A is going to roll all the way to the top. A3 is going to roll to a point symmetric on the other side, and so on, right? But they will all take the exact same amount of time to complete their cycles. So let me show you what I mean there. This is kind of a good, no, not that one. This one. This is kind of a good illustration of that. So I'm starting these particles at 2 different points on this inverted cycloid. And if I start them, you'll see they reach the halfway point, because that's half of their period at the same point, and then they finish out their cycle in the same amount of time. And so this actually became really important in clockmaking, because that's how they decided to use a pendulum for like a grandfather clock. So they set the pendulum to be on an inverted cycloid path, and then no matter where you start the pendulum, it will trace out the same amount of time no matter what, right? And that way they could make all these grandfather clocks the same, because it didn't matter the way you sent them. You just started the pendulum, and all clocks were basically telling the exact same amount of time that way, because they were all ticking on an inverted cycloid, and thus ticking through their period in the same amount of time.